evening, everybody. My name is Isaac Montoya, and I am the Director of Marketing here at Uptime Technologies. First and foremost, I would like to thank you all for joining us here today for week 2 of our 6th annual Airflow Management Awareness Month. We started this kind of initiative back in 2015 with really the hopes to raise awareness around airflow, but also around cooling optimization and data center efficiency in general. And we are, very thankful to have received a lot of support from all of you and a lot of people in the industry, and we're glad to be here for our 6th year to share some good educational webinars with you. I'd also like to quickly note, if you'll notice at the top right of the screen as well as at the bottom, you'll notice it says 20 years of optimizing data center cooling, and we here at Upsite are celebrating 20 years as a company, and we would just like to give a special thanks to all of our valued partners, resellers, and customers for helping us make it this far. I'll be joined here shortly by Lars Strong, Senior Engineer and Company Science Officer here at Upsite Technologies, who will be headlining today's webinar. Before I pass it off, I would like to go over a couple quick housekeeping items. So everybody will be muted throughout the duration of the webinar, but we do encourage you to ask as many questions as possible, and you could do so through the Q&A module, and we will get to those at the end of the webinar in the Q&A portion. If you have any technical difficulties, please send me a message through the chat module, and I will try to get that resolved for you as quickly as possible. As I mentioned, this is week 2 of our annual Airflow Management Awareness Month. Last week, we were joined by Mark Acton, Independent Consultant and Non-Executive Director at EchoSense, who gave a great presentation on data center energy efficiency and sustainability. If you happen to miss that, please feel free to shoot me a message in the chat, and I can provide you with a link to where you can watch that on demand. Next week, we'll be joined by Bill Clayman, Executive Vice President of Digital Solutions at Switch, who will discuss the perimeter-less data center and touch on security, automation, and robotics. In the 4th and final week, we'll be joined by John Gross, owner and engineer at JM Gross Engineering and ASHRAE contributor, who will discuss what's new in ASHRAE's 5th edition of thermal guidelines and how it can impact your facility. If you haven't registered for those sessions, we'll be providing a link a little bit later in the webinar for you to do so if you'd like. Now, a little bit about Lars. Lars is our resident expert here at Upsite Technologies. He's also a recognized expert in the industry, and he has over 20 years of experience in airflow management and cooling optimization. He also holds many certifications, a couple of which being HVAC and IT specialist from the U.S. Department of Energy as a data center energy practitioner. Lars has spoken at many industry events such as Data Center World, Data Center Dynamics, and many others where he has discussed a broad range of topics, as you'll see here on the slide. As for today, it's worth noting that this topic is of much discussion and debate, with the biggest question always being, should I contain the hot aisle or the cold aisle? We've covered this topic on the Upsite blog, and it continues to be one of our highest viewed articles, even though it was originally published back in 2014. So we know this is a topic that many of you are interested in, and we hope that we can generate some good discussion here today. And again, we encourage you to ask as many questions throughout the webinar, and we'll make sure to get to those in the Q&A portion of this presentation. Now, without further ado, I'll pass it off to Lars to get us started.
Well, thank you very much, Isaac. I'm very excited to be here today and to share my knowledge of cooling containment and optimization. And we got a lot to cover. Well, let's get started. This is the agenda that we're going to go through. We're going to talk a little bit about the 4 R's of airflow management and how that can help guide you. We'll talk about some of the lesser known best practices and then some common best practices. We'll talk about the science of containment and look at the options available for containing your hot or cold aisle. And then really importantly, we'll take a look at the cooling optimization process and look at the benefit of the fan laws and the 4 delta T's and how those can help you in identifying opportunities for improvement. So let's jump right into it. The 4 R's of airflow management is a concept that we developed to help people focus their efforts on airflow management improvements and cooling optimization. There's the 3 R's around the outside of the circle here in this graphic show the various areas that airflow management can be improved. sealing openings in the raised floor horizontal plane, sealing openings in the vertical plane of the racks, and then improving airflow management at the row level. And this is what we'll be focusing on today. Now, each of these has an arrow pointed into the room, which indicates that there is an opportunity after any improvements are made at any one of these three R's to look at the room level and make adjustments to the set points and the controls to realize benefits and improve the efficiency and capacity in the room. And we'll talk more about that towards the end of the presentation. So focusing today on row airflow management, this is simply the process of separating the hot and separating the cold air from the hot air at the row level. Some of the less commonly known considerations there are blocking open spaces underneath racks. This is important for preventing flow underneath the cabinets. We'll look at that in more detail. And sealing spaces between cabinets. So for hot aisles, row airflow management generally involves some form of ducting the exhaust air back to the cooling units, installing doors and baffles or a full chimney up to a drop ceiling plenum, and then ducting the cooling units to the drop ceiling. For cold aisle containment, it's a little simpler, simply attaching doors and then some form of baffles or potentially a full roof over the top of the cabinet. So hopefully everyone on the call has a hot and cold aisle configuration established in their facility. There's very few locations where there's still some legacy layout of cabinets all facing in the same direction. Hot and cold aisle is absolutely crucial for achieving efficiency and crucial for the implementation of hot or cold aisle containment. And one of the challenges with cooling optimization is that air is invisible. And while we might think that since we've done hot aisle containment or hot and cold aisle configuration in a room, that this is the way the airflow looks in the room. However, it's often much more like this. Cold air being delivered to the cold aisle, but potentially some unsealed openings under the cabinets, potentially some misplaced perforated tiles, allowing conditioned air to leave the raised floor space where it's not needed into a hot aisle. And then there's numerous forms of exhaust recirculation, potentially through the cabinet. Rack airflow management addresses blocking recirculation through the cabinet. But then there's potential for exhaust air recirculating over the tops of the cabinets and around the ends of the cabinets. And this is what row airflow management addresses. So this is the goal, to only have the cold air delivered to the cold aisle, no mixing, no loss of cold air into spaces where it's not needed, just pure separation. And to get there is an incremental process that I'll reference numerous times through this presentation. It's not a one and done. There can be numerous projects to incrementally make improvements as you get closer and closer to the ideal. So let's take a look at some of the little details that you need to pay attention to when addressing row airflow management. Underneath the cabinets. So the space where the leveling feet or the casters are creates an opening at the bottom of the cabinet for exhaust air to circulate under the cabinet. This CFD analysis shows that the warmest intake temperatures to these cabinets are at the bottom of the cabinet, not at the top. Having hot spots in the tops of the cabinets is fairly common, but numerous times I've found with my infrared camera surveying rooms that the hottest locations in the cabinet are at the very bottom because of exhaust air circulating through this open space. And when it's sealed, the equipment has the ability to draw in the conditioned air being supplied from the supply tiles and intake temperatures to drop. So these changes, from existing conditions to having those openings sealed in this image, there were no changes to the tile configuration or the temperature or the volume of conditioned air or fan speeds. The only change that was made was sealing those openings, and that dramatically dropped the intake temperatures to the IT equipment. Another very important space to address is any space between cabinets. These can be very small spaces, like an inch wide, when cabinets just are not butted up against each other, or a much larger space such as this, where a column has interrupted the row and a cabinet can't be placed there. Again, CFD analysis is showing how exhaust air is circulating through this space, coming into the cold aisle, and elevating the temperatures along the edge of the cabinets. Sealing this space that can be done with a rack gap panel, a product of ours, or a number of other different solutions, blocks that path flow, that path for exhaust air, allowing the conditioned air that's being delivered to the aisle to do its job. You can still see at the tops of the cabinets, there's a little bit of air still circulating over the top of the cabinet right now, and that would be addressed by airflow management across the tops of the cabinets at the top of the aisle. Another important consideration and a challenge that many data centers face is having uneven rows. And it's very hard to put doors on an aisle end if the cabinets are not at the same length, if they don't match up. So we have a product called an adjustable mounting post and a rack gap panel that can seal that. There's a number of ways to extend this row out and seal that space so that doors can be attached, so the rows can be evened up and doors can be attached to contain this aisle. An important step to take just to make sure that everything is uniform and can be addressed. Pardon, the screen is frozen up for a moment. I'm having to restart PowerPoint. I've never had that happen. I apologize. So, picking up where we left off, let's look at some of the commonly known best practices and what most people think of when they think of airflow management at the row level and data center containment. So primarily this involves, and the first step is always to install doors at the ends of the aisle and contain either the hot or the cold aisle. As I mentioned, this is the first thing you want to do. It can reap significant benefits, even if that's all you do. If you have a limited budget, just putting doors on the ends of the cabinets can block that exhaust air recirculation around the ends of the row and significantly improve conditions. Here's a few examples of what doors are available. There's bidirectional doors. These swing in and out and attach magnetically. There's a wide variety of sliding doors available on the market. This one has a transom above it to match the height of the cabinets. There's single hinged doors. These typically swing just out and hinge on one side. And then of course, we all know about curtains. And although they've got a lot of problems, they do solve some very challenging situations where it's conditions make it very difficult to install a door on the end of an aisle. So then moving on to the top of the cabinets, we're talking about rack top containment. This is typically necessary when the highest levels of efficiency and capacity from the cooling infrastructure are desired. And this can be done in a number of ways, either with just some partial baffles or with a full roof. In a hot aisle configuration, this would be baffles or ductwork up to the drop ceiling, and then ducting the cooling units up to the drop ceiling to create a complete path for that exhaust air to return to the cooling units. So here's again some examples of how that looks and what the options are. Here on the left, we have a ceiling with rigid panels. So this is a rigid frame, and these panels are sensitive to temperature, and in the event of a fire, they become flexible and lose their structural integrity and just drop out of the ceiling frame. And for partial containment, when a quicker and less expensive solution is desired, is modular or racktop baffles. These are rigid baffles. They don't move. They attach magnetically on tops of the cabinets, and they block the exhaust air flowing over the tops of the cabinets. And they also contain the cold air, but they leave enough space for gaseous fire suppression to enter the aisle and for sprinklers to get some water into the aisle. So in most cases, these are approved by the local authority having jurisdiction. There are national fire codes, but the local authority is the person, your fire marshal is who you need to check in with on any of these solutions to make sure that they approve of what you're doing. For hot aisle containment, here's some examples. This would be a chimney sitting on top of the cabinets and going all the way up to the drop ceiling. This dark image here shows a cooling unit extension. This is essentially a chimney on top of the cooling unit, but the air is going the opposite direction. Obviously, it's flowing through the ceiling plenum and then down into the cooling unit. And then here's the modular or the partial containment example for hot out containment, which just has vertical baffles. And these just help direct the hot air towards the ceiling where the ceiling registers are going to be and the hot air can enter. This solution, or even without these vertical baffles, simply ducting the cooling units to the drop ceiling and installing doors on the ends of the aisle can get a great deal of benefits. I've heard some people say, 80% of the benefits of full hot out containment can be achieved just by putting doors on the ends of the aisle and a ceiling plenum return. Whether that's going to be 80 or 70 or 90% of the benefits of full containment depends on the unique conditions of your facility. And happy to get into those unique conditions and details of application in a offline conversation if you like. So let's look at the science of airflow management, because this is really where the rubber meets the road, where the benefits can be realized. Of course, by putting in airflow management at the row level, doing, installing all the things that we've talked about, you're going to see some improvements in the intake temperatures to IT equipment. And that has a financial benefit of improving the reliability of the equipment. But as far as the cooling optimization goes and realizing OpEx gains from higher efficiency, you're going to have to do some optimization. There's some benefits to both the hot and the cold aisle, and there's some challenges to both hot and cold aisle. Let's talk about those a little bit more. So for hot aisle containment, the open area of the room is left cold, and that has some advantages to it. Leaks from the raised floor space or other openings in the room are leaking conditioned air, excuse me, into the cold area of the room. And so it doesn't enter the room as bypass airflow. It is actually available for cooling the equipment. Hot aisle containment is generally more effective because it's implemented more fully. So studies have proven that both cold and hot aisle containment are equally efficient if implemented fully. And that's a big if. With hot aisle containment, it's easier to implement that fully than doing cold aisle containment. Hot aisle containment is more forgiving for network racks and other standalone equipment because the rest of the room is a cooled environment. And so you can place equipment out in that space and it's going to be a cool environment available to provide a little bit of cooling for things that need airflow from a non-standard perspective, not front to back like a hot and cold out configuration. And it's possible to design a hot out containment without making adjustments to the gaseous or the sprinkler fire suppression systems. In a lot of jurisdictions, that chimney to the hot aisle is not considered a space that needs to be covered by gaseous or by fire suppression. But you need to, again, check with your local authority about that. So some of the benefits of cold out containment is that it's much simpler to implement. It only requires doors at the ends of the aisles and then potentially some baffles or a cap on the aisle. And so that's why we see the cold out containment as being much more common because it's much simpler to implement. And for those reasons, it's generally less expensive to implement. And obviously easier to retrofit. Cold aisle containment doesn't absolutely need to be on a raised floor. It can be done with a slab environment and overhead delivery. The overhead delivery is just obviously done to the contained cold aisle. One of the major benefits of cold aisle containment is that there's more surface area for cold sinks. And I have got that backwards on these slides. For hot aisle containment, the benefit is that you have more cold sinks, more surface area. The bulk of the room is cold and there's more surface area, more mass that is maintained cold. So that's gives you more ride through in the event of a cooling failure. Apologize for that mistake. We'll correct that before we send the slide deck out. Some of the challenges of hot out containment are obviously just the reciprocals. It requires a contained path for the air back to the cooling units. So this requires a drop ceiling. Some sites don't have that, so that's generally not an option for them. It's generally a little more expensive. It may require modifications to the fire suppression system. More gas may be required for gaseous fire suppression to address that additional volume of the return ceiling plenum. And it creates a very hot space for people to work in that hot aisle. But that's true of any form of containment. If containment is done well and cooling is optimized, then there will be a hot space. It'll either be the hot aisle or it'll be the rest of the room. Some of the challenges of cold aisle containment, the remainder of the data center becomes hot, as I just mentioned, and it can be dramatically hot. I've entered a data center where this was done very well. They had cold aisle containment, but when you walked into the data center, it was 95 degrees in the rest of the room. That can be a challenge for some. It makes it hard for standalone equipment to be cooled. Equipment that doesn't fit in that hot and cold out configuration is going to be out in that hot space. Conditioned air leaking from the raised floor enters now the exhaust air path back to the cooling units, and that lowers the efficiency. So sealing the raised floor becomes very critical. And it requires more considerations of fire suppression, drop away panels, and potentially for containing that cold aisle, you might have to use a mechanical louvered system that opens up. It's tied into the smoke detection system, and the louvers, the ceiling opens up when a smoke detection occurs. So this is what it looks like, obviously, to do full hot aisle containment. This picture from before, we've got the cold air coming out into the rest of the room. It's flowing around all through the room. If you have too many tiles in one location, that air can make it to where it's needed. And then the hot air is contained, ducted to the ceiling plenum and back to the cooling units. For partial hot out containment, we just have those baffles or potentially no baffles at all. And the air, if volumetric flow rate of conditioned air is balanced well, there will be the natural path of this exhaust air to flow to the ceiling and back to the cooling units, reaping most of the benefits, as I mentioned, of full containment. Cold aisle containment, here's rigid, obviously with a full ceiling over the cold aisle. Cold air is only delivered to the cold aisle, and so all the intake temperatures in the cold aisle should be very uniform. This enables the supply temperature to be raised quite high. If your maximum inlet temperature is, say, 80 degrees, then it's possible to have supply temperature of 75 degrees or higher without exceeding a maximum intake temperature of 80. So that can become a very efficient scenario. Partial containment with the baffles enables you to get very close to the full containment solution, just a little easier to implement. So let's now talk and get into some of the details of optimization. So what is optimization? Airflow management is managing the air movement through the room. Optimization is the process of making adjustments to the cooling system controls to reap the benefits of energy efficiency and reduce operating costs, improve cooling capacity, and defer capital expenditure. This can, this is a big list. It's a very important list. There's a lot of money left on the table by people who have made improvements and not done the optimization process to realize those benefits. Said another way, cooling optimization is the goal of that is to provide the appropriate IT equipment intake air temperatures and relative humidity, and redundant cooling capacity with the lowest possible flow rate of conditioned air at the warmest possible temperature. So reduce fan speeds as much as possible and raise set points as much as possible. And the more airflow management that is deployed in a room, the more this can be achieved. It's often an iterative process. Like I mentioned in the beginning, it's not one and done. You get to, each time you make improvements, there's opportunities for adjustments and optimization. Then you make more improvements to airflow management, more optimization, as well as each time there's any significant change in the room, like a significant addition of IT load or removal of IT load, then there's an opportunity for optimization. All important scenarios to be paying attention to. And as I mentioned before, just to drive it home, without optimization, airflow management improvements are primarily an expense. You will see some benefits of intake temperatures and reduced flow rates, fan speeds in the IT equipment, but primarily it's an expense. You got to make these adjustments to realize the benefits and see the ROI. Said another way, you can't purchase efficiency. Efficiency has to be managed. So let's take a look at a very important concept for this process. And it's one of my favorite things to talk about. I think really helps people get the grasp of airflow management in the room, and that's bypass airflow. So in this scenario, this room, we have 10 units of air, the volumetric flow rate, often measured in CFM, of all the air moving through all the cooling units in the room is 10 units in this example. So 10 units of air goes out from the cooling units under the raised floor. And if you add up all the air coming out of all the openings in the raised floor, it will be 10 units of air. In this case, we have 6 units of air coming out of intentional openings, supply tiles in the cold aisle. And we have a total of 4 units of air coming out of unmanaged, unsealed cable openings under cabinets or out in the hot aisle. So you could say, well, there's 4 units of bypass airflow. Well, that looks like the case. However, you need to consider the demand flow rate of all the IT equipment compared to the delivered flow rate. So we have 6 units of air delivered into this cold aisle. But if you look at the demand flow rate of conditioned air through all the IT equipment in this row, it's 2 units. And in this row, it's also 2 units. So the IT equipment has a demand flow rate of 4 units of air. 6 delivered, 4 gets sucked up by the IT equipment. We have 2 excess units of conditioned air. This is also bypass airflow. But without containment, this extra air is necessary to keep the exhaust air recirculation from causing hot spots. So in this room, we have 6 units of bypass airflow. So we want to seal these openings. Of course, that's best practice. That gets all the conditioned air into the cold aisle, but it doesn't actually change the amount of bypass airflow. We're delivering 10, the IT equipment still only needs 4. So 10 minus 4 leaves 6 units of bypass airflow, conditioned air that never flows through IT equipment, returning to cooling units. But managing the airflow in the room, putting in containment, enables us to then reduce the fan speeds and realize those benefits. Now we can deliver 5 units of air, 1 unit extra, a little extra for slight positive pressurization and variations in IT load. Now we can optimize either by turning off half the cooling units or turning down the fan speeds. And so let's look at that. What are the benefits of turning down the fan speeds? Well, there's fan affinity laws. And what these different graphs show are the effect of turning down fan speeds on the flow rate, the pressure, and the power consumed by the fan motors. So if you reduce the fan speed by just 10%, you will reduce, sorry, if the fan speed is reduced by 10%, the flow rate will decrease by 10%. If you reduce the fan speed by 10%, the pressure will drop by 19%. It's the square of the fan speed. If you reduce the fan speed by 10%, then the energy consumption of the fans will decrease by 27%, the cube of the fan speed reduction. And this gets very dramatic. If you reduce the fan speed by 50%, you reduce the energy consumption by 87%. So dramatic improvements in OpEx can be realized by reducing fan speeds. And this is the lowest hanging fruit in the room. Took just a moment to take a drink of water there. So let's look at this last concept, and this is the 4 delta T's. Now, most people, when you ask them how many delta T's are there in a computer room, most people will say, well, there's 2 delta T's. Obviously, there's the change in temperature of the air as it moves through the IT equipment. That would be delta T1 here. And there's the change in temperature as the air moves through the cooling units. The temperature is dropping, obviously, delta T3. And as the air comes out of the cooling units, it really shouldn't heat up much before it gets to the intakes of the servers. And when the air comes out of the servers and flows back to the cooling units, the air shouldn't cool off very much. And this is what an ideal scenario would look like. The air is delivered at around 70, 75 degrees, and maybe it warms up a little bit. A small delta T is expected. The air might warm up to 80 degrees for a maximum, and that's represented by these colors here. And then the air comes out of those servers at 95, 100 degrees, flows back to the cooling units and cools off a little bit. Maybe it drops down to 90, 95 degrees. A little bit of cooling, a little bit of excess bypass airflow is understood, is reasonable. And that would give you a 20-degree delta T through the cooling units and approximately a 20-degree delta T through the IT equipment with no change in temperature at these other 2 locations. However, this is often what we see. Conditioned air is being delivered at a much cooler temperature. Often it's 55, 60, maybe 65 degrees supply air. And then that air warms up significantly to the warmest intake. There will be locations in a cabinet where the intake temperature is very close to that supply temperature of 60, 65 degrees. And then there will be locations where the intake temperature is much higher. And by the way, ASHRAE's recommended minimum intake temperature is 64 degrees, 64.6 degrees. So a supply air temperature below that is creating cold spots by ASHRAE's definition. So any ability to raise the supply temperature is going to improve the efficiency and capacity of the room. And then very often we see exhaust temperatures, of course, and the around 90, 100 degrees, but the return air temperature to the cooling units is typically, around 70 degrees. Used to be 64 is a common set point for return air. That's increasing, maybe 70, 72 in some sites perhaps, but it's much colder than it came out of the cabinets. Why is it colder? Well, it's because of exhaust air recirculation. I'm sorry, it's because of bypass airflow. Excess conditioned air that didn't pass through IT equipment mixes with the exhaust air and cools it before returning to the cooling units. And why is the air warming up when it comes out of the supply tiles? It's because of exhaust air recirculation. So the goal of improving airflow management in your facility is to get these two less common delta T's, delta T4 and delta T2, down to about 5 degrees. So the air should only warm up about 5 degrees from the time it leaves the cooling unit to the warmest intake, and cool down about 5 degrees from the exhaust temperature of the IT equipment back to the cooling unit. Now there's some caveats to this. There's variations in delta T through equipment and such, but these are general guidelines. And these are very easy delta T's to measure and identify opportunities for improvement. So let's talk about a few key takeaways. And if you haven't yet typed in any questions, please do that. We're going to have plenty of time for questions. So row level airflow management it's not all about containment. There's a number of other important areas to address. And a big challenge I see in a lot of computer rooms I visit, they've already implemented hot or cold out containment, but they haven't done something as simple as install blanking panels in every open use space. So that's leaving money on the table, meaning optimization cannot be as complete, cannot go as far. OPEX cannot be reduced as far as it could be if blanking panels were installed, even though you have full containment installed. So addressing all of the basic fundamental prerequisites of airflow management are really important to getting the most out of cooling optimization and row level containment. Modular containment is extremely effective at reducing temperatures and creating the opportunity for optimization. A number of sites have not implemented some containment practice because they feel like full containment is too expensive and beyond their means. But I hope you recognize now that just adding doors or baffles on tops of the cabinets is a much lower cost solution and doesn't require some of those expensive adjustments to the fire suppression systems. And so it's much more attainable than you might have realized and can produce significant benefits. In situations when cabinet densities are high or the highest level of efficiency is desired, you want to get that PUE as low as possible, then rigid or full containment is the best option. It also is the best option for challenging environments where a room is an unusual shape or there might be a low ceiling. Cooling units are placed in less than ideal locations, creating some bad airflow patterns in the room. Then full containment is probably going to be more necessary for achieving that efficiency. And then, can't say it enough, optimization needs to be part of your airflow management improvement process. You need to provide, of course, appropriate IT intake temperatures. You never want to compromise on that. Whatever you've established for your maximum IT intake temperature, you need to manage that too. But with improvements to airflow management, it's possible to raise the control set points substantially in many cases without increasing the intake temperature to the IT equipment. So huge benefits can be realized through this process. I hope this has been very valuable to you, and we'll get into some of your questions now to see what you're wondering.
All right, thank you, Lars. It was a great presentation. I just want to remind everybody, we do talk about a lot of these topics on our blog. So please feel free to follow us on our blog or on LinkedIn or any of our other social media platforms for our latest conversations all around airflow management and cooling optimization. All right, let's jump into the questions. Lars, are there any scenarios in which no containment at all is an effective solution?
Well, yeah, that's a question a lot of people bring up, is they feel like they have done the hot and the cold aisle configuration and they probably don't need to do much of anything more. This often goes along with saying, I don't have any hot spots. I'm cooling my equipment effectively. I don't have a problem. And that's, I have no argument with that. That's the case. They are effectively cooling the equipment. However, without containment, it requires higher flow rates of conditioned air, higher fan speeds, and lower temperature set points to keep the IT equipment happy. So there's no scenario where not having containment is the most efficient possible. You can get the job done, but it won't be as efficient as it could be if you installed some level of containment.
All right, thank you. Let's move on to the next one. So we actually have a couple questions. We have one asking about the raised floor, and a similar question: what's best for rooms with overhead supply?
With overhead supply, then it's really important to contain that delivered air to the aisle and create a space for that conditioned air to drop into, and then let the exhaust air flow freely back to the equipment. That's generally the most common way that's done, but it can also be done the other way. It's important to point out that hot and cold aisle containment are essentially the same thing. It's a barrier between the hot aisle. It's a barrier between the conditioned air and the exhaust air. It just where you put it that we're talking about. So in any scenario, you can find a way to achieve that. And before you continue, I'll just say one of the common things that we see is a slab environment with a flooded supply. And in those environments, it's very crucial to do hot out containment and let that conditioned air flow around the room, flood the room, but you've got to contain that exhaust air and get it back to the cooling units without letting it mix. The least efficient rooms I've seen are those with flooded supplies, but without containing the exhaust air.
Got it. Thanks, Lars. Let's move on to the next one. Is it necessary to install booster return air fan for better circulation?
Yeah, that's another good question. So what I've said throughout my career is that probably 85% of fan-assisted supply tiles sales are unnecessary. There are scenarios, low raised floors, lots of cable blockages before doing cable mining and clearing up the space, odd corners of the room where just that conditioned air is not getting to, the static pressures under the raised floor are low for whatever reason. And booster fans or fan assisted supply tiles are really crucial for getting some conditioned air out of the floor in those locations. But in most cases, the amount of air coming out of all the supply tiles can be increased passively without adding electrical load, which, fan assisted tile adds some heat to the room. It can be done by very thoroughly managing the open area of the raised floor by sealing all the cable openings, openings around electrical equipment, making sure supply tiles are in the right locations, just making sure there's no leakage from the raised floor where it's not intended. That can dramatically improve airflow through the supply tiles and negate the need for the booster tiles.
Got it. Thank you, Lars. Next one, hot out containment. If no drop ceiling, would ducting hot out air up to the ceiling or all the way back to the AC return be a workable option?
So two parts to that. One is if there's no drop ceiling, no common space for the return air, then it's possible to put some baffles to direct the air upward, and that can create some significant benefits. It prevents the hot air from flowing over the tops of the cabinets. But as far as putting in ductwork to contain the air back to all the cooling units, that's certainly possible. The most cost-effective way is with a drop ceiling, just a single horizontal plane to separate those two spaces. But it could be done with ductwork. The challenge is in making that ductwork large enough and doing the configuration such that the air is going to flow back to the cooling units appropriately and not mostly flow back to a few. That it'll be distributed evenly among the cooling units is a challenge. So that kind of a scenario is very rarely implemented.
Got it. Thank you, Lars. When we have containment, do we consider the containment area for cooling calculation or the room area?
I'm not sure I understand the question. Yeah, I don't understand the question. Read it one more time. Okay. I'll try again.
When we have containment, do we consider the containment area for cooling calculation or the room area?
Yeah, we'll have to take that one offline. I don't quite understand the question. Apologize for that.
Okay. Moving on to the next one. Is it necessary to raise top of ceiling unit, crack or craw, higher than the cabinets so as to improve the hot air circulation?
Yeah, I appreciate this question. This is something that is done to improve the conditions in the room. It's kind of and it might address one of the previous questions too. It's kind of an interim step. If you don't have a drop ceiling, but you do have high ceilings, one thing that can be done is to put extensions on the cooling units. And that means that they're going to be drawing their air from higher up in the room. The air is hotter next to the ceiling, and it also changes the direction of the air flow through the room. So without a cooling unit extension, the air in the cold aisle might be drawn towards a cooling unit return and pulled prematurely from the cold aisle. But when you put an extension on a cooling unit, 3, 4, 5 feet, could be tall, or even in rooms with higher ceilings, that air is going to flow up, go across the face of the cabinets, get sucked up by the IT equipment, then go into the cold hot aisle. And the hot air from the hot aisle is going to be more likely to flow up, and it's going to be less likely to flow over the tops of cabinets, causing problems in adjacent cold aisles. So yes, long answer to your question, cooling unit extensions in an open room can definitely improve the environment, both the intake temperatures, equipment, and the efficiency of the systems.
All right, thank you, Lars. Moving on to the next one. While doing IST or load tests using rack-mounted heaters, do we need to consider delta T of the load bank unit?
Yeah, so in a commissioning process of doing load bank testing, load banks generally have a significantly higher delta T than IT equipment, most IT equipment. But that's okay because they have a lower flow rate of air. So the combination of flow rate and delta T gets you an average that can simulate what's going on in the room. And so, answer your question with a straight answer, yes, you do need to consider it. It's not necessarily a problem, but you do need to look at what the flow rate is through the load banks and what the delta T is through the load banks, and see how that will match an averaged out compared to the IT equipment you plan to install in the room.
Got it. Thanks, Lars. We have
Yeah.
a ton of great questions coming in. We're going to try to get to all of them. We got about 8 minutes left here. So we're just going to keep moving on. Next one, Lars. Can we have both hot out and cold out containment to optimize the cooling unit and avoid hotspots?
Yeah, so it's possible. Some people have done both. Some measures that would be seen as hot out containment and cold out containment in the same room. It's generally unnecessary. You just focus on one location or the other, and that creates the separation from the hot and the cold aisle. There may be unique scenarios where you do a few things on the cold aisle and you do a few things on the hot aisle, but that comes down to a case-by-case basis, generally with irregularities and one-off layouts in the room. For a very symmetrical, clean room, you don't need to do both. You do one or the other.
Got it. Okay, let's move on to the next one. What about in-row cooling solutions offered and delta T measurements in such a scenario?
Thanks for bringing up in-row cooling units. Not something I addressed specifically in the presentation. A lot of what I discussed applies. In-row cooling units are often deployed in a mixture with other standalone or other hot and cold aisle configuration equipment with standard raised floor supply. And so it's not a straightforward answer as to which is best to do, hot out containment or cold out containment for those in-row scenarios. In-row cooling units can handle or can be made very efficient with either cold out containment or hot out containment. Generally, in-row cooling units require full containment, though, a rigid ceiling, because the flow rates are so high. The fan speeds or the air velocity coming out of the in-row cooling units is so high, it's very turbulent, and it'll flow across the aisle, hit the other side, and spread up and leave the aisle very easily if it's not fully contained. So that addresses hot and cold out considerations. As for delta T, and considering the 4 delta T's, the same thing applies. The goal is to have the supply temperature coming out of in-row cooling units as closely matched to the maximum inlet temperature of the IT equipment as possible. Improving airflow management will enable those set points to be raised, and that enables the return air temperature to those in-row cooling units to increase, and then the in-row cooling units become more efficient. And also, most in-row cooling units are made with variable speed fans, and so the fan speed can be also adjusted. And the same goals apply: reduce the fan speeds of those in-row cooling units as much as possible to match the demand flow rate of the IT equipment in that aisle.
Great, thank you, Lars. How much air efficiency is lost using cabinet bottom or top panels with brush grommets for cable and power with pass-throughs?
I believe I understand the question. So yeah, using brush grommets for cable pass-through as opposed to a full solid brush grommet is very little difference in the efficiency. The brush grommets for cable pass-through are very effective at blocking airflow from the front of the cabinet to the back. There's usually very little pressure difference from the front of the cabinet to the back of the cabinet. And that brings me to a related point that I want to make, which is, how do you know if you're delivering the right amount of air to a cold aisle? Well, if you have a fully contained cold aisle, and you open the door and air rushes out, cold air blasts out of that cold aisle when you open the door, you're delivering too much cold air to that aisle, excess cold air. Full containment does not guarantee airflow balancing. It just guarantees no exhaust air recirculation, but fan speeds still need to be adjusted so that when you open the door, there's a very slight positive pressure in the aisle compared to outside the aisle, and a little bit of cold air flows out of the aisle when you open the door. If you open the door and hot air gets sucked into the cold aisle, then you're not delivering enough conditioned air to that cold aisle, but that's rarely the case. Just to make this point really clear, I was on a site that had installed curtains for full cold aisle containment, and they said the curtains didn't work because they were blowing out sideways, you know, like Marilyn Monroe's skirt, they're flapping in the breeze. And what they did was they took out the curtains, put in rigid containment, and they thought that that had solved their problems, but they hadn't adjusted fan speeds. So they were still wasting conditioned air. It just wasn't obvious to them. The right thing to have done was they could have left the curtains in place and just turned down fan speeds or taken out supply tiles, adjusted the amount of conditioned air coming into the cold aisle until the curtains slowly came down and were hanging just slightly, you know, vertical. That's an indication of balanced airflow.
All right, thank you, Lars. Okay, let's move on to another one. This one's an easy one in terms of modular containment. Can we install vertical top rack baffles for cold containment or the angled ones?
Yeah, so the angled baffles are the most common appropriate solution for cold aisle containment. The only exception for that is overhead delivery to cold aisle. Then you want to use the vertical baffles just to create kind of a bathtub to hold that cold air as it dumps in and a larger open space to receive that conditioned air. But angled baffles are the appropriate solution for cold aisle containment with a raised floor delivery.
All right, thank you, Lars. Is there any solution to contain an open rack in a cold aisle containment row?
Open racks like 4-post racks or 2-post racks are generally a challenge. I was in a facility just a couple weeks ago, and they had a large number of these, but they did find a way to install blanking panels in the 2-post racks, and then use some rack gap panels to seal the spaces from the 2-post racks to the adjacent full cabinets. So there are some ways to do it. It can be tricky, especially with the large cable management systems that are generally associated with those. We've done some custom solutions of some 6-inch brushes that stood vertically to address that. It can be done, but unique conditions need to be considered.
Got it. Thank you, Lars. Probably got time for maybe one, maybe two more. So let's just keep going here. For an existing rack layout in the same direction, what would be the estimated savings in ROI to the changes to either hot or cold aisle containment? 150 racks, average 3 kilowatts per rack.
So there's no way for me to really give you a number. It's going to be based on how much you can reduce fan speeds primarily from us changing the equipment to a hot and cold aisle configuration. But that's a very hard thing to do. I've not seen many sites where the ROI warranted the cost of going in and switching all the cabinets around as a project. Most often what is done is, as cabinets are decommissioned, then the new cabinet is put in the appropriate configuration. And it's a mix and it's a mess for a while until cabinets get replaced. Obviously, a factor in this is the rate of refresh. But any facility, probably, every facility should have a floor plan with the ultimate goal of what they want the room to look like that's going to achieve the greatest efficiency. And then anytime something is decommissioned, take that as an opportunity to move the room towards the ultimate goal.
All right, thank you, Lars. I think that's going to be all we can do for today. I apologize to anybody that if we did not get to your questions. We'll make sure to follow up with you directly here after the presentation. For those of you asking about these slides, we will be sharing the slide deck as well as the recording of this webinar with you here in the next day or two. So keep an eye out for that. We'll also share some links to register for our webinars over the next couple weeks. Thank you all for joining us, and Lars, thank you for a great presentation. I think there's a lot of really great information in here.
Thank you. Thank you, everyone, for your time.